Lectures 1 and 2 of this module, we introduce some general concepts of solutions, the energetics of solution formation, and how to deal with specific concentration units of various solutions. In this lecture, we want to talk about a concept called colligative properties, which specifically means we're going to look at the properties of the solutions, especially compared to just the properties of the solvents that they're made out of. If you dissolve a solute in a solvent to produce a solution, there are several properties of the solution that are different from the pure solvent that you used. So, for example, suppose we prepare two different aqueous solutions of equal molalities. The first solution would be a 1 molal solution of glucose in water, and it would be prepared by dissolving 1 mole, which would be 180 grams of glucose in 1 kilogram of water. That's why it's a 1 molal solution, 1 mole per kilogram. Our second solution will be a 1 molal solution of sodium chloride. And this solution would be prepared by dissolving 1 mole of sodium chloride, which in this case would be 58 grams, in 1 kilogram of water. So we have these two solutions. So what we're going to ask is, what properties of these solutions would be different than the pure solvent water that was used in their preparation? Well, some of these properties would be obvious. The first would be each solution would weigh more than the original pure solvent. So for example, each solution has 1 kilogram of water, so the pure solvent weighs 1,000 grams. The 1 molal solution of glucose would weigh 1,180.15 grams because we added 180.15 grams of glucose to the 1,000 grams of water. And the mass of the 1 molal sodium chloride solution would be 1,058.44 grams. And both of these numbers are just consistent with common sense. Adding solute is going to increase the mass of each solution relative to the mass of the original pure solvent. So we see one way in which the solutions are definitely different than the solvent that we started with. Another thing that would be different about each solution is that each solution would have a greater volume than that of the original pure solvent. So for example, the volume of the water that we started with would be 1001.8 milliliters. You might ask how I know that. Well, what I did was, knowing the density of water at 20 degrees C, I could calculate what the volume of water would be for 1,000 grams of water. I had density data for both the glucose and the sodium chloride solutions. And so I calculated from experimental data that the volume of the glucose solution would be 1,114.4 milliliters. The volume of the sodium chloride solution would be 1,019.9 milliliters. Now, the fact that both of these solutions have volumes greater than about 1,000 milliliters, and that when you make the solutions, both solutes just seemingly disappear into the water. Remember, when you make a solution in water and things dissolve, the solution doesn't look any different than the water by eye. So the added solute molecules actually take up some space. So each solution would have a greater volume than that of the original pure solvent. The other thing is that the solutions are more dense than the original pure solvent. The density of pure water is just barely under 1 gram per milliliter. The density of a 1 molal solution of glucose is just above 1 gram per milliliter. And so for also for sodium chloride solution, the sodium chloride solution is not quite as dense as the glucose solution. Now, interestingly, these densities, both the densities of the solutions are higher than the density of the water, and you might think, well, that only makes sense. You've added all that solute. Well, remember, the volumes of each of these solutions is greater than the volume of the original water, so it's not a sure bet that their densities would be higher, but they are. Let's look at some more differences between the properties of each solution and the pure solvent, and we'll list these on the next slide here. It turns out that each solution has a lower freezing point than the original pure solvent, water. The freezing point of water, of course, is 0 degrees C. The freezing point of a 1 mol solution of glucose is minus 1.92 degrees C. And the freezing point of a 1 mol solution of sodium chloride is minus 3.43 degrees C. So notice that despite the glucose and sodium chloride solutions both having equal concentrations, at least equal molalities, the freezing point depression, meaning the drop in the freezing point, of the solution of the ionic compound, sodium chloride, is nearly twice as great is that of the solution of the molecular compound, glucose. Just keep that in your head for a few minutes. Most important thing so far is that solutions have lower freezing points than the pure solvents that they're made out of. We can express this freezing point depression in equation form. We can say delta TF, that would be the freezing point depression, is equal to the freezing point of the solution minus the freezing point of the solvent. Since the freezing point of the solution will be lower than the freezing point of the solvent, delta TF turns out to be a negative quantity. Each solution actually will have a higher boiling point than the original pure solvent. So for example, the boiling point of water, as you know, is 100 degrees C. The boiling point of the 1 mol glucose solution is 100.5 approximately, and of sodium chloride 100.9. So again, both solutions have higher boiling points than the original pure solvent. They both show boiling point elevations, but the boiling point elevation for the sodium chloride is about twice as high as the boiling point elevation for glucose. Boiling point elevation for sodium chloride is 0.9 degrees because that's how much higher it is than the pure solvent, and it's 0.5 for the glucose. If we were to write this out in an equation, the boiling point elevation would be the boiling point of the solution minus the boiling point of the pure solvent, and since the boiling point of the solution is higher because they undergo boiling point elevation, that delta TB would be a positive quantity. The other thing that's different about each solution is that the vapor pressure of water vapor over each solution is lower than the vapor pressure of water over the original pure liquid water solvent. The vapor pressure of water vapor over pure liquid water at 20 degrees is 17.54 torr. The vapor pressure of water vapor over the solution of glucose is 17.2 approximately, and that of water over the sodium chloride is about 16.9. So there's a vapor pressure lowering for both solutions, and consistent with what we saw for the freezing point depression and the boiling point elevation, the effect seems to be about twice as large for sodium chloride solution as for the glucose solution. And again, we're looking at the vapor pressure lowering. So the vapor pressure is lowered about 0.6 torr for sodium chloride and about 0.3 torr for the glucose. Again, if we were going to express this in an equation, we'd say the vapor pressure lowering is equal to the vapor pressure of the solvent over the solution minus the vapor pressure of the pure solvent. And delta P here would be negative. Vapor pressure lowering is most likely the least interesting to you on the list here. However, this vapor pressure change for solutions turns out to be the basis for explaining why each solution freezing point is depressed and each boiling point elevated relative to the pure solvent. So we're going to spend a little time talking about vapor pressure lowering of solutions compared to the vapor pressure of the pure solvent. Freezing point depression, boiling point elevation, and vapor pressure lowering are collectively known as colligative properties. So there's the title of each one of our slides in this lecture, colligative properties. Colligative properties are properties that depend on the number of solute particles dissolved in the solution. And as I said, we want to spend a little time on vapor pressure lowering, so let's get to discussing that. Now we can use the preparation of the 1 molal glucose solution to rationalize why the vapor pressure would be lower over the solution than over the pure solvent. Here's a cartoon that's supposed to represent a beaker with liquid water in it, and the liquid water is evaporating to water vapor, and then the water vapor is recondensing to the liquid. In other words, we've reached equilibrium in here, and we can signify that with this equation, H2O liquid in equilibrium with H2O vapor, and when this occurs, the vapor pressure, the pressure of the water vapor over this pure water would be 17.54 torr. This picture doesn't really show the beaker as being sealed completely, which it should be, but we'll ignore that for now. Let's dissolve some glucose, and I've made the glucose red because in the next picture these red spheres are supposed to represent the glucose molecules dispersed in the liquid water, and now we have, instead of pure water, we have a 1 molal solution of glucose. Well, what effect does that have on this liquid vapor equilibrium? Well, the particles dissolved in the solution take up some space on the surface of this solution, and for a little while it slows down the evaporation of water. So we have a shorter arrow going up from liquid water to water vapor, and you can see in the cartoon this arrow is shortened here. And what that does is, for a short period of time, we don't know exactly how long, the condensation of water vapor is faster or occurs at a higher rate than the evaporation of liquid water to the vapor. And so what you start doing is depleting the vapor phase here of water molecules. And when equilibrium is reestablished, which it will be, there are fewer water vapor molecules above the solution. So we've got equilibrium reestablished, but when it does, the vapor pressure of the water vapor over the solution is now lower than it was over the pure solvent. We can actually think of vapor pressure lowering as an entropy-driven phenomenon. And here's something that I thought was a clever explanation. Recall that chemical systems tend to move toward states of greater disorder. We talked about how a positive delta S is something that would naturally drive reactions or processes. So when equilibrium is established for the pure water here, there's enough water vapor to satisfy the disorder requirement at the stated temperature. If we dissolve some glucose in here, this results in increased disorder in the liquid phase, so the resulting 1 mol solution requires less water vapor molecules to satisfy the same disorder requirement at 20 degrees C. Less water vapor molecules means lower vapor pressure. Now, entropy here, of course, is the quantity we keep saying we want to put off discussing until later in the course, but we seem to not be able to stop discussing it. Now, vapor pressure lowering can be described in a more quantitative manner using something called Raoult's law. Let's look at that on the next slide. If you recall from an earlier slide, the expression for the vapor pressure lowering for a solution was the following: that delta P is equal to the vapor pressure of the solvent over the solution, that's P of solution, minus the vapor pressure of the solvent over the pure solvent. And of course, delta P here is the vapor pressure lowering, and since the vapor pressure of the solvent over the solution is less than the vapor pressure of the solvent over the pure solvent, delta P will always be negative. You can get the vapor pressures of the pure solvents usually from tables of data where these have been obtained. The vapor pressure of the solvent over the solution can be obtained from an equation that describes the principles of Raoult's law. One way we can write this is that the vapor pressure of the solvent over the solution is equal to the mole fraction of solvent in that solution times the vapor pressure of the solvent over the pure solvent. This can get to be a little bit confusing, so let me restate it another way. How much the vapor pressure is lowered depends on what fraction of the molecules in the solution are actually solvent molecules. So if you dissolve more and more solute, the fraction of molecules that are solvent will drop, and so it will cause the vapor pressure to drop. The more solute you dissolve, the more the vapor pressure drops. Also, you might recall from slides 2 and 3 that we stated that the vapor pressure of water over the solution of 1 mol glucose would be around 17.2 torr compared to 17.54 for the pure solvent. So let's see if we can get a vapor pressure of water over the solution of 17.2 using this expression for Raoult's law. Well, I'm going to rewrite Raoult's law right here, and then for water we could rewrite the expression so it looks like this. The vapor pressure of water over the solution is equal to the mole fraction of water in that solution times the vapor pressure of pure water. We know the vapor pressure of pure water at 20 is 17.54, so we need to determine the mole fraction of water in the solution. So recall the solution was made by dissolving 1 mole of glucose in a kilogram of water. So what I'm going to do is simply find out how many moles of water are in a kilogram of water, or in 1,000 grams. I'll do that by dividing 1,000 grams by the molar mass of water, and we find out that a kilogram of water contains 55.509 moles of water. So if we want to calculate the mole fraction of water, it'd be the number of moles of water divided by the number of moles of water plus the number of moles of glucose. Well, the number of moles of glucose is 1, because that's how we made the solution. So it turns out that the mole fraction of water in the solution is 0.9823. The solution is mostly water if you actually are counting things, and that makes perfect sense. The solvent is water. Therefore, the vapor pressure of the water over the solution would be this mole fraction of water, 0.9823, times the vapor pressure of pure water, and we get a number of 17.23, or in other words, very close to the number that we said it should come out to be, 17.2 torr. So the vapor pressure lowering is thus the vapor pressure of the solution, 17.23 torr, minus the vapor pressure of the solvent. So we've just said the vapor pressure lowering is minus 0.3 torr. That's how much the vapor pressure dropped compared for the 1 mol solution of glucose compared to the vapor pressure of water over just pure water. Now let's apply Raoult's law to calculate the expected vapor pressure lowering for the other solution we discussed, the 1 mol solution of sodium chloride. So you might ask, wouldn't we just get the same result for the 1 mol solution of sodium chloride as we did for the glucose? Yeah, but let's do the calculation anyway. Raoult's law is written here. Vapor pressure of water over the solution would be the mole fraction of water in the solution times the vapor pressure of pure water. We know the vapor pressure of pure water. Let's determine the mole fraction of water. In this solution, we have 1 mole of sodium chloride per 1,000 grams, 1 kilogram of water. If we convert the 1 kilogram of water to moles, we get a very familiar looking answer. If we calculate the mole fraction of water in this solution, we get a very familiar looking answer. And therefore, the vapor pressure of water over the solution would be the mole fraction times the vapor pressure of pure water, and we get 17.23 torr, or about 17.2 torr. So the vapor pressure lowering is simply minus 0.31 torr. Now remember, this is what we would get by using Raoult's law. And again, the result came out to be exactly what we got for the 1 mol solution of glucose, which shouldn't be too surprising since we used very similar numbers. Well, exactly the same numbers. So this is a hardly surprising result. There is a minor problem here in that this is wrong. And when I mean wrong, the calculation's correct. It just doesn't reflect reality. It turns out that the vapor pressure of water over the 1 mol solution of sodium chloride is not 17.2, it's 16.9, which means that the vapor pressure lowering for sodium chloride solution is not minus 0.31 as calculated from Raoult's law. It's actually about minus 0.6. So the vapor pressure lowering for sodium chloride solution is in reality almost twice as large as that for the glucose. And remember, we're amazed at this only because the solutions are of the same molality. Well, maybe we can explain this. Sodium chloride is an ionic compound which dissociates an aqueous solution into two particles, sodium ion and chloride ion. So if you take 1 mole of sodium chloride, which is what we did here, and dissolve it in water, you're going to get 1 mole of sodium ions and 1 mole of chloride ions. And as you recall from General Chemistry 1, sodium chloride, when it dissolves in water, acts as an electrolyte. It breaks up into ions that can conduct electricity in the solution. So sodium chloride is an electrolyte, and for this particular ionic compound, you get 2 ions for every 1 formula unit that dissolves. Glucose, on the other hand, produces just 1 particle in solution for every glucose molecule that goes in. 1 mole produces 1 mole of solid glucose produces 1 mole of aqueous glucose. Glucose is a molecular compound. It hangs together as a molecule in solution. It does not break up into particles or ions. And the fact that it does not break up into ions reminds us of the fact from General Chemistry 1 that glucose would be considered a non-electrolyte. So if you recall from slide number 2 that the vapor pressure lowering is a colligative property, one that depends on the number of solute particles in solution, it makes sense that 1 mole of the ionic compound sodium chloride, which produces 2 moles of particles in solution, would have double the effect on these colligative properties than 1 mole of glucose, which just produces 1 mole of particles. Now, at high concentrations of ionic solutes, something called ion pairing can affect the results. So in other words, here we seem to be able to say that it makes sense that the effect for sodium chloride would be twice that of glucose, because sodium chloride breaks up into 2 ions for each sodium chloride that dissolves. Later on, we'll find that when the concentrations of the solutions become larger, that the ionic compounds have some unexpected behavior that we can adjust for. We'll get to that in a few slides. Before moving on, I want to point out some cautionary statements about vapor pressure lowering of solutions and application of Raoult's law. One of the things you want to keep in mind here is that we carefully limit ourselves to cases involving only non-volatile solutes. Well, what's a non-volatile solute? Basically, a non-volatile solute, which is what we used here, both glucose and sodium chloride, have pretty much zero tendency to evaporate under the stated conditions of the experiment. We can show this with our cartoon of glucose dissolving in water. If you recall, we had a beaker of pure water with liquid water in equilibrium with water vapor. When we dissolved the glucose, and you can see the glucose dissolved in the liquid water, it turned out that to disturb this equilibrium between liquid water and water vapor, but when equilibrium was reestablished, there were fewer water molecules above the solution than there were above the pure solvent. Well, you already know this. What am I trying to point out here? I want you to notice that there are no red spheres in the vapor phase. We're only talking about a drop in the water vapor pressure. We don't have any of the glucose molecules in the vapor phase. In other words, the glucose is non-volatile. It does not have any tendency to evaporate. Now, if it did, it would complicate our life. So we're going to assume that for all the examples that we do, that the solute is non-volatile. Now, what would be an example of an aqueous solution containing a volatile solute? If you dissolve methanol in water, and it does dissolve quite readily in water, you'd have a solution, of course, of aqueous methanol. However, methanol itself is quite volatile. It evaporates easily. And if that would be the case, some methanol vapor would mix with the water vapor over the solution. And again, what that would mean is that in this diagram here, we'd have red spheres mixing in with the water in the vapor phase. This would complicate application of Raoult's law in the limited way that we have described. So we're going to avoid those situations. We will only be dealing with non-volatile solutes. The other thing that we supposedly are doing is we limit ourselves to cases involving only ideal solutions. Ideal solutions are defined as solutions where all the intermolecular forces, the solvent-solvent, the solute-solute and solute-solvent intermolecular forces are identical. Well, knowing what we have discussed earlier in this course about the various types of intermolecular forces in operation in a solution, you might suspect that no real solution is ideal. Therefore, what we're going to say is that we need our solutions to at least approach ideal behavior, meaning that specific solvent-solvent, solute-solute, or solute-solvent intermolecular forces do not have an outsized influence compared to all the other intermolecular forces operating in solution. Suffice it to say that you're not going to really need to worry much about either one of these cautionary statements, but I just want to point out that we're applying Raoult's law to a limited set of circumstances that are fairly well defined. Now let's take a couple of minutes to examine how the vapor pressure lowering actually causes a decrease in the freezing point and an increase in the boiling point of a solution relative to that of the pure solvent. So how does vapor pressure lowering result in freezing point depression and boiling point elevation? Well, let's first look at boiling point elevation, and to do that we'll use a generic phase diagram. If you recall, phase diagrams show the conditions of pressure and temperature under which a substance exists as a solid, liquid, or gas. This particular phase diagram looks a little busy, and the reason is because the black lines represent the boundary lines, phase boundary lines, for the pure solvent. So in our examples here, we could say that this is the phase, these are the phase boundary lines for water, since water was our solvent. Now keep in mind here that the liquid gas phase boundary line basically shows the vapor pressure of the pure liquid solvent increasing with temperature. And so at each one of these temperatures, this would be the vapor pressure, for in our case, of water in equilibrium with liquid water for just pure water. So this is the vapor pressure for pure water. The blue lines are phase boundary lines for the solution. So we can say, okay, this is for our glucose solution. We saw that the vapor pressure is lowered, so the vapor pressure of the water vapor over the solution is lower than the vapor pressure of the water over the pure solvent. And so we see a vapor pressure lowering. So we see this blue line here is lower all the way across all these temperatures than the line for the pure solvent. Again, black would be pure water, blue would be the water, say, glucose solution. Well, so what that the vapor pressure was lowered? Well, what that means is that you have to heat the solution to a higher temperature to get the vapor pressure of the water over the solution equal to atmospheric pressure. Because remember, boiling point is defined as the temperature at which the vapor pressure equals atmospheric pressure. So since the vapor pressure is lowered for the solution, you actually have to heat it to a higher temperature to get its vapor pressure equal to atmospheric pressure. So the boiling point of the solution is higher than the boiling point of the solvent. And I've marked on the diagram below on the temperature axis the change in boiling point would be the boiling point of the solution minus the boiling point of the pure solvent. Delta TB is positive. You get a boiling point elevation. Now let's examine how vapor pressure lowering results in freezing point depression. So as I said, let's examine the freezing point depression using the same generic phase diagram as on the previous slide, only it's marked up just a little bit differently. Recall again that the black lines are the phase boundaries for the pure solvent. In this case, it would be for us for pure water. And the phase boundary lines for the solution are in blue. And again, this could represent, say, our 1 molal glucose solution. And we can see that the vapor pressure is lowered from the pure solvent to the solution. Well, what does this mean? Well, as this curve drops here, it causes the solid liquid line to move to the left for the solution. And since the solid liquid line represents the freezing point of the liquid, we can see that the freezing point of the solution is now lower than the freezing point of the solvent. And I've marked on the diagram below here that this lowering of the freezing point, delta TF, which would be the freezing point of the solution minus the freezing point of the solvent, delta TF would be negative. There's a freezing point depression associated with the solution as compared to the pure solvent. You'll also notice that the triple point of the solution is depressed compared to the triple point of the pure solvent.